Hello everyone, today let's take a look at QP number 76, another conditional probability question and kind of a follow-up to QP number 6. So we have two players A and B who alternately toss a fair coin, and the game ends as soon as a sequence of heads followed by tails occurs, and then the player who would have flipped that tails would win. So if A goes first, what's the probability that he wins? And again, there's infinitely many ways to play this game. For instance, A could flip tails and then B could flip tails, A could flip tails, B could flip tails on for like a million times, and then maybe A flips a heads and then B flips a tails, and then the game's over, right? So again, when you're solving this question, it's basically a Markov chain, a stochastic process. It's best to just draw out a state transition diagram. So what are the different states that we have in this question? So let's start off with the state that A wins the game, and this is going to be an absorbing state in our Markov chain. Again, you don't need to know what that means yet because we'll talk about that later, but it's just basically where the game ends here. And the way that A wins the game is when they flip tails when they face a heads and it is their turn. So I'll denote that as A sub H. So again, if A ever faces a heads from the opponent and then they flip a tails, they win. And that happens with 1/2 probability when they're given a heads, right? Now instead, if A flips a heads, well then we'd go over to the state where it's B's turn and they're facing a heads. So I'll call that B sub H, and that happens with 1/2 probability as well. And from this state, B could win the game if they flip a tails when they face a head. So I'll call this one over here B wins, and this happens with 1/2 probability when we're in this state. Also, if we're player B and we're facing a heads, well then we also have a 1/2 probability of flipping a heads ourselves too. So there's a 1/2 chance that we go back to the state where A is facing a heads. But we also have two more states, right? We have the state where A is facing a tails and the state where B is facing a tails. So what's the probabilities for these? So if it's our turn and we're player A and we're facing a tails, well, we obviously have a 1/2 chance of flipping either a heads or a tails. So with 1/2 probability, we go to the state where B is facing a heads if A flips a heads, right? And if A flips a tails, well, then we go with 1/2 probability to the state where B is facing a tails. And if we're B facing a tails, we have 1/2 probability of flipping tails. So back to A with the tails, and we have 1/2 probability of flipping heads. So back to A with the heads. So this is just a nice way to visualize what's going on, and it makes this problem a lot easier to solve. So you can see that if A flips a tails and then B flips a tails and A flips a tails, we go around in this loop for however long, but as soon as one of them flips a heads, we end up in one of these states, and when we're up here, there's no going back down here, because as soon as one of these players flips a tails when they're facing a heads, well then they're going to win. So it's A's turn first, so what state do we actually start in this problem? So what you realize about this game is that all that really matters in terms of winning is what the last flip was. If the last flip was a heads, well then a tails ends the game. But if the last flip was a tails, well then no matter how many flips that have happened before where everything was tails, right? You're going around in this cycle right here. You're in the exact same situation as if you just started the game. So for that reason, when you start the game, that's just like being in the state where you're facing a tails. So now basically what the question is asking is that given that we start in the state, what's the probability that we end up in this one instead of this one? Basically all we have to do to solve this is just find the probability that we win from each one of our states, all of which will depend on each other, and then we kind of solve that system of equations for this one right here, and we'll end up with a number. So let's just write it out real quick. I'll call the probability of A sub t the probability that A wins from this state, and we know that that's equal to 1/2 of the probability that we win from this state, because we go to that state with 1/2 probability, right? So I'll say 1/2 times the probability of B sub t, or we could go to this state up here. So we add on 1/2 probability that we go to that state, which is B sub H. Also, it's going to get confusing later in the video. This is me from the future, but when I'm referring to the probability of A sub t or the probability of B sub t, that's the probability of A winning from that state. It's not the probability of that state happening. It's the probability that A wins from that state. Okay, now if we're in the state of B and we're facing a tails, well then now what's our probability that A wins in this situation? Well, we have a 1/2 probability of going to this state up here, so 1/2 times the probability of A sub H. And we have a 1/2 probability of going back to A sub t. So we add on 1/2 times the probability of A sub t. And you can keep going like this. When we're in this state, A sub h, well, our probability of winning is 1/2 because that is over here, right? So we have 1/2. And then we add on 1/2 probability that we go over to B sub h, so plus 1/2 times the probability of B sub h. Now finally, if we're in this state, B sub h, that's just going to be player B's turn when he's facing an h from player A. Well, from this state, we lose with 1/2 probability, so no need to count that, but we can only win if we go back to this state and then we win from this state. So this is just equal to the 1/2 chance that we go back to that state times the probability that we actually win from that state. Okay, now it's gotten a little complicated, but all we need to do is just to solve for this, because this was our starting state, right? So we just solve the system of equations. I can plug this in over here, and when I I do that, I get that the probability of a sub h is equal to 1/2 plus 1/2 times this, which is going to give me 1/4 times the probability of a sub h. And when I subtract that over to the other side, I get that 3/4 times the probability of a sub h is equal to 1/2. So the probability of a sub h is equal to 2/3. So that tells me when it's my turn and I'm in this state where I'm facing an h from player B, then I win 2/3 of the time in the long run, basically. Then I can plug this number in right here, and that tells me that the probability of player A winning when it's B's turn facing an h is equal to 1/3. Okay, so now this is getting a little bit complicated, but I can just plug this one right here in over here. So I get that the probability of B sub t is equal to 1/2 times the probability of A sub h, which is going to be 2/3. So that's going to give me 1/3 here, and then I add on 1/2 the probability of A sub t. Okay, now finally I can plug this one in up here, and then I can plug this term in right here, and then we'll be able to solve for this probability. So when I do that, I get that the probability of A sub t is equal to 1/2 times this right here, which is going to be 1/3 plus 1/2 times the probability of A sub t again. And then I have over here, I have 1/2 times the probability of B sub h, which is 1/3. So that's going to be 1/6 that I'm adding on right here. Now just to simplify the right hand side, I get 1/6 here, and I'm going to get 1/6 over here, so that's going to be 2/6, which is 1/3, and then when I multiply this 1/2 by this term, I get 1/4 times the probability of A sub t, and that was all equal to the probability of A sub t, so now I can just solve for this. So when I subtract this to the other side, I finally get that 3/4 times the probability of A sub t is equal to 1/3. So what does that tell me? That tells me that the probability of A sub t is equal to 4/9, which is what we were trying to get originally. So that means player A, when he starts, wins 4/9 of the time in this game. Also, I must note that there is a much easier way to solve this specific problem right here due to the nice properties of symmetry in it. Basically, you can see everything in this problem is symmetric. It's a lot easier when you visualize it too, but even these are all the same probability for each player. So what does that mean? Basically, what you notice is that the probability that A wins from this state right here is going to be equal to the probability that B wins from this state. So the probability that A wins from this state is equal to 1 minus the probability that B wins from this state, obviously. But the probability that B wins from this state was equal to the probability that A wins from this state. So therefore, we can just write this term right here as 1 minus the probability that A wins from this state of t. Now also another symmetry that you could have noticed that would have made your life a little bit easier is that the probability that A wins from this state was equal to this value right here, right? And with this value, we were dealing with the probability that A wins from this state. Well, the probability that A wins from this state is equal to the probability that B wins from this state over here. And the probability that B wins from this state is just equal to 1 minus the probability that A wins from this state, right? Which is equal to this right here. So we can just plug in right here 1 minus the probability that A wins from that state. And then using that, we would solve for this and we get 2/3 again, and then we'd get that B sub h is equal to 1/3, and then you just plug everything in using this and you'd get the exact same answer. So yeah, sorry that got so convoluted, but basically all you need to know is just how to draw out these diagrams and then calculate these probabilities. And again, we'll do a lot more when we actually get to Markov chains, right? But the answer in this case was 4/9. Also, you can solve this problem with the infinite geometric series, but this way is just going to be a lot easier to think about, especially when these start to get more complicated.